Today we're going to look at triple integrals, which are a natural extension to double integrals. To motivate triple integrals, we computed mass and charge of things like plates, and we pretended that they were very thin, infinitely thin, and so we could just do it over 2 dimensions. In reality, that's not true. So we want to compute integrals of a density over volumes. And what this means is we're going to have to generalize everything we did from 2 to 3 dimensions. And so particular, our little area Aij is now going to become a little volume cube, Vijk, which of course also depends on 3 scaling vectors, n, m, and now l. And so the first 2 dimensions of Vijk are exactly the same as Aij, but we now have a third dimension, and that dimension is in z, and it goes from p plus k minus 1 over l times q minus p up to p plus k over l times q minus p. And these volumes now run over I 1 to n, j 1 to m, and k 1 to l. And now we can define the triple integral, which is identical to the definition of the double integral, except for now it's over 3 variables. So the triple integral of f of x, y, and z over some bounded region E is defined as the limit as the minimum of n, m, and l go to infinity of this triple sum, so now we have triple Riemann sums, of f evaluated at a point in the box x star ijk, y star ijk, z star ijk, times this little volume increment Vijk. F is said to be integrable when this limit exists and is equal for all different choices of points in the box. Again, when F is continuous and it's defined on a compact, meaning closed and bounded set E, it is integrable. The standard properties of linearity, monotonicity, and disjoint that we explained in double integrals just hold. They hold in exactly the same way, so we won't list them out and we won't prove them, but they hold in exactly the same way. Also, to get the volume of a set, we just substitute in density F is just 1. Once again, we have Fubini's theorem, but now for 3-dimensional objects. And for that, we again assume that F and E are both bounded and measurable. And when that is true, we can integrate in any order. So for example, if we let FE be F times the indicator, then we could first integrate from P to Q of FE dz, and then we could integrate from C to D of FE dy, and then finally we could integrate with respect to x on the outside. But we could reverse the order. We could do x first, and then y, and then z, or any of the 6 different possible combinations could be done. And that all of these are equal to this integral that we just defined over the 3-dimensional region E of f x, y, z dv. Once again, measurability is beyond the scope of this course, but includes things that are almost continuous. So things that maybe are continuous except for on the boundary of these indicator functions. When E is a rectangle, things become particularly simple, and we know by changing f, we could always make that the case. But let's take a look at this example. The density of gold is given by rho of x, y, z is equal to 1 over 1 plus x plus y plus z in ounces per meter cubed. And then we're asked how much gold is there in the box E is equal to 0 to 1 cubed, meaning 0 to 1 in each dimension. To solve this, we need to recall a few little integration by parts-based formulas. The indefinite integral of ln is x ln x plus some constant. The indefinite integral of x ln x is x squared over 2 times ln x minus a half plus some arbitrary constant. So to find the gold, we need to integrate this density over this region E, which is this rectangular region. And by Fubini's theorem, we can do it by this triple iterated integral. And so we can take rho 1 over 1 plus x plus y plus z and integrate it first with respect to x and then y and then z, all from 0 to 1. And it's not going to matter the order of integration because this problem is completely symmetric. So we're going to use antiderivatives 3 times. And we can do that all in one step as long as we plug back in the exactly right way. We can ignore the constant because we're going to be using the definite integral, so it's the constant will cancel out. So an antiderivative for 1 over 1 plus x plus y plus z is, of course, ln of 1 plus x plus y plus z. And then an antiderivative of that is 1 plus x plus y plus z times ln of 1 plus x plus y plus z. And then finally, an antiderivative of that, we use the x ln x formula, and we have 1 plus x plus y plus z squared over 2 times ln of 1 plus x plus y plus z minus 1/2. This is good, but after the first antiderivative, we were just letting x represent these two values, 0 and 1. And then after the second antiderivative, we were just letting y represent the two values, 0 to 1, and then finally z, the values 0 and 1. And so we have to be careful we get enough terms when we do it this way. You really should plug into this formula first all x's are 1 and then subtract all x's are 0. Do the same thing with y. Then after that, you'd get 4 terms. Plug in y is equal to 1 and then y is equal to 0. And then finally, for each one of those terms, plug in z is equal to 1 and then negatively z is equal to 0. And you'd wind up with a total of 8 terms. However, due to symmetry, it's really just important to keep track of the sign and how many of the x, y, and z are 0 and how many are 1. So in particular, if we had all of x, y, and z 0, then we only have one of those terms, and that would be a negative term because we'd be evaluating x at 0, y at 0, and z at 0, so it would be a triple negative, which becomes negative again. And for the first factor here, with x, y, and z being 0, we'd have 1 squared over 1, which is 1/2. Then we'd have ln of 1, which is 0, minus 1/2. But we had a negative to start with, so that would turn into a positive 1/2. Now, when 2 of the x, y, and z are 0 and 1 is 1, then we'll have 3 of those terms, because there's 3 possibilities of which could be 1. And then the 1 plus x plus y plus z squared becomes 1 plus 1 squared over 2 is 2. So we'll have 3 terms times 2. Now we just have to evaluate what's in there, and it's going to be ln 2 because 1 of x, y, and z is 1, and then minus 1/2. And now we'll go back to negative when only 1 of x, y, and z is 0 and 2 are 1, and we'll have that we have 3 of those terms because only one of them is 0. So there's a 3, and then 1 plus x plus y plus z squared is going to turn into 9, so it's going to be 3 times 9 over 2, and then we're going to have ln of 3 because 2 of x, y, and z are 1 minus 1/2. And when all of them are 1, you evaluate it positively. So we're going to have 1 plus 1 plus 1 plus 1, which is 4 squared over 2 is 8. And then we're going to have ln of 4, and then we're going to have minus 1/2. And this can simplify out fairly easily to 3 plus 22 times ln 2 minus 27 over 3 ln 3. We use types again to account for non-rectangular E. So in type ZA, we suppose that we can decompose E, the region of space, into XYZ such that XY is in some region of the plane D, and then Z is restricted to be between PXY and QXY. So this means that it's not necessarily rectangular. But we can still use this type to simplify the triple integral into a double integral and a single variable integral, in that the triple integral over E of fxyz dv is a double integral over D of the single variable integral from pxy to qxy of fxyz dz dA. But now think of that inner integral, the integral from pxy up to qxy of fxyz dz, as a new function of just x and y. The z has been integrated out. Call that gxy. And D might be of type yx. So this area integral, the double integral of D of g of xy dA, may also be broken up into an integral from a to b of an integral from cx to dx of gxy dy dx. So then, recalling how we define g, we can substitute that back in and substitute the area integral into the volume integral, and we wind up with the triple integral over region of space E of fxyz dv is equal to the integral from a to b of the integral from cx to dx of the integral from pxy up to qxy of fxyz dz dy dx. If we had a different type, say type xy for the area integral, so overall we would have type zxy, then the volume integral over E of fxyz dv would be the integral from c to d of the integral from ay to by of the integral from pxy up to qxy of fxyz dz dx dy. Notice as we go into more and more inner integrals, they can depend on more and more variables. The outer one never depends on any variables. The next one from the outside can depend on the one variable that we have left to integrate, and then by the time we go on the inner side one, it can depend on all but the variable we're integrating out. So with this last formula, which we could call volume by type zxy, we're really integrating heights first from pxy to qxy. That would look as u1xy up to u2xy in this picture. And then we integrate across depths from ay to by, which would be denoted h1 to h2 in the picture. And then finally we go from c to d. Also notice that this idea is very similar to our earlier idea of volumes by slicing, where we wrote the volume of a solid was the integral from c to d of ay dy, where ay was a slice of area. This was encountered earlier, but the exceptions that we have now is that there's a density in A, and also A was computed by integrals, but it has the same form, and it's not necessarily volume. We could go through similar procedures. Instead of starting with type ZA, we could have had type YA, and would result in this formula. We could have had type XA, and would result into this formula. In both of these cases, we could also take subtypes over D. So we would wind up with types like YXZ and YZX. And then for the type XA, that could be type XYZ and type XZY. So the strategy is to divide the volume integral into few integrals of these different types. So let's take an example just so you can see all the different types that you could wind up with. So a solid is defined by x is greater than 0 and x squared plus y squared plus z squared is less than or equal to 1, i.e. it's bounded by a plane and a sphere. It has density rho x, y, z is equal to x. Express the mass m of E, which is given by this triple integral over E of rho x, y, z dv in all 6 orderings and solve the integral. Okay, so let's first think of constraining x. So x has to be above the plane x is equal to 0, so it must be at least 0, and has to be below the sphere. The sphere has the equation x squared plus y squared plus z squared is less than or equal to 1. On the boundary, we have equal, and the constraint on x to be below the boundary is it then must be less than the square root of 1 minus y squared minus z squared. Remember, it's non-negative because it's above the plane. And so now we have to constrain y and z so that this even makes sense. So we need y and z to be in some region D of the plane such that the square root of 1 minus y squared minus z squared is non-negative. And that is simply that y squared plus z squared is less than or equal to 1. Now we can express that as a constraint on z and a constraint on y, where this constraint on z has to depend on y. So we could make z range from minus the square root of 1 minus y squared up to the square root of 1 minus y squared. And then we could just let y range from minus 1 to 1. And if we substitute these into the type xzy formula, we have that me is equal to the integral from minus 1 to 1, the integral from minus square root of 1 minus y squared up to the square root of 1 minus y squared, the the integral from 0, because it must be above the plane, up to the square root of 1 minus y squared minus z squared of rho, but rho is just x, dx, dz, dy. A very similar argument, just switching the constraint in d from y to z, we would get type x, y, z is the integral from minus 1 to 1 of the integral from minus the square root of 1 minus z squared up to the square root of 1 minus z squared of the integral from 0 up to the square root of 1 minus z squared minus y squared, x, dx, dy, dz, different order. Let's consider constraining y first. There's no plane constraint on y. It just has to be within the sphere. So that means that y can be between minus the square root of 1 minus x squared minus z squared and the square root of 1 minus x squared minus z squared. Now, x and z are going to have to be in some planar region D, and that's going to have to account for the fact that x has to be non-negative. So D has to reflect the fact that we're in a sphere, and so the constraints on x and z are going to be the maximum circle. So we're going to have x squared plus z squared is less than or equal to 1, but we also have that x has to be non-negative. And so this means that x can be between 0 and the square root of 1 minus z squared, and then z can be from minus 1 to 1. So this would result in type y, x, z, where the mass of E is given by the integral from minus 1 to 1 of the integral from 0 to the square root of 1 minus z squared of the integral from minus the square root of 1 minus z squared minus y squared up to the square root of 1 minus x z squared minus y squared, x, dy, dx, dz. And similar arguments result in the three remaining types that we list here. Let us move on to evaluating the integral. And to evaluate it actually makes most sense to use polar coordinates for y and z, because they're always constrained to be inside some type of circle. And so we could make E be the x, r, and theta so that r squared is less than or equal to 1 minus x squared. So we've set r to be the square root of y squared plus z squared. And so then r squared is less than or equal to 1 minus x squared is the constraint to be below the sphere. And we still have the constraint x is greater than 0. And so if we evaluated this as type theta rx, that would be the easiest thing to do. So m of E then is a constraint on x, which is just simply that it's between 0 and 1, because 1 is the maximum value it could get on the hemisphere. And then we have the constraint on r, which is that it goes from 0 up to the square root of 1 minus x squared. And there's no constraint at all on theta, so it can just go from 0 to 2 pi. Then we have our rho, which is x, which we do not need to convert because their polar coordinates are in y and z. Then we have r d theta, dr, dx. Well, since there's no dependence on theta, the integral from 0 to 2 pi d theta is just the integral of 1, which is just 2 pi. And then the integral of r, so we're going to get an r squared over 2 as an antiderivative, which we have to evaluate positively at the square root of 1 minus x squared, which is going to give us 1 minus x squared over 2. Then we have an x, so we multiply that out by x. And so we're left with the outer integral from 0 to 1 of x times 1 minus x squared over 2 dx. Well, just making the substitution now that u is equal to 1 minus x squared, we wind up that that's 1/4 of the integral from 0 to 1 of u du, which is equal to pi over 4. So let's finally talk about applications. So just like in 2 dimensions, the standard applications that we're discussing here are mass, charge, moments, and moments of inertia. So when we talked in 2 dimensions, we use terms like laminar thin plate, but in 3 dimensions, we look at real objects that are solids. So volume, for bounded and measurable E, there is a Cartesian product of closed intervals, AB, cross CD cross PQ, which contains E. So we can evaluate the volume integral as the integral on this cross product AB cross CD cross PQ of 1E dV. And because it's a cross product there, we could use Fubini's theorem to separate them out as in any order we want, and then we use the indicator 1E to come up with the type that we will use to evaluate it. For charge, there's bounded, measurable sigma and E. So now we have a function. And since E is bounded, there is this Cartesian product again of closed intervals that contains E. And the charge on E is the triple integral of E of sigma dV. And it can be written out also as the integral over AB cross CD cross PQ of sigma. But now we have to add the indicator function because otherwise you'd be integrating over too large an area to restrict it back. For mass, there's another separate density, rho, which now is normally non-negative, and the same thing holds since E is bounded and measurable. There's a Cartesian product, and we can write out the mass in exactly the same way as we did for the charge just above. Our last applications are related to moments for solids with mass rho, say. So about planes, we have the moment my, which is the triple integral of z rho xyz dv. It's the moment about the xy plane, and that could be evaluated as before by getting a larger rectangular set and then restricting and using Fubini's theorem when you evaluate over the larger rectangular set. And we have similarly the moment xz about the xz plane. So notice for xz, we're integrating y times rho of xyz dv. So the one that's not in the plane, so outside of the plane variable. And then finally, we have the moment in the yz plane, which is myz, where we're integrating x times rho dv. The center of mass then is defined as the x bar, y bar, z bar, which is the cross moment over the mass. So x bar is the moment about the yz plane over the total mass. And similarly, y bar and z bar are defined. The centroid is a center of mass where rho is a constant. And since rho is a constant, it can be brought out of the integrals on the numerator and the denominator. And so we're left with x bar is a triple integral of x dv over the triple integral of E dv. So obviously the bottom one is just the volume of E. Y bar is a triple integral of y dv over the triple integral dv, which is just again the volume of E. And similarly for z bar. The moment inertia about the axes then are the Ix is the triple integral of y squared plus z squared all times rho of xyz dv. That's the moment inertia about the x-axis. Notice we left x out. The moment inertia about the y-axis has x squared plus z squared, leaving y out. The moment inertia about the z-axis has x squared plus y squared, leaving z out. Thank you.